Another aspect to the latent heat of change that we don't generally think about a huge amount is what they do out of the Bureau of Meteorology and everywhere around the world when they're measuring the relative humidity. And we're going to have a look at what they call the Stevenson screen, which is a box where all these measurements have been measured for well over 100 years, and the box is designed to have consistency right around the world. But at this stage we're just going to have a look at and see one of the measurements they're actually measuring inside the Stevenson screen, and that is they've got two thermometers. Now I've replicated what they've got inside the Stevenson screen here. We need to have one thermometer that is just measuring the air temperature, and we've got another one that is quite unique in the fact that it's actually got a container of water and it's drawing water up through a wick, and that wick is surrounded in the bottom of the bulb of a second thermometer. And what that is doing is surrounding that bulb with moisture. So the moisture is taken up through capillary action and surrounding that bulb. Now the latent heat of change of that water vaporizing or evaporating off that bulb reduces the temperature of that second thermometer. And so you get a variation in the two measurements between the dry thermometer and the wet thermometer. And in this case we're going to have a look, and we can see on our dry thermometer we've actually got a temperature of 13.5 degrees Celsius, and our wet one is 9.5 degrees Celsius. So we've got a change or a variation in temperature. So just to show you these, the water inside the glass passing up a piece of tissue, and that is surrounding that other bulb, and that is evaporating. So as it's evaporating, that is cooling down that second thermometer down to 9.5 degrees Celsius. The other one is measuring the real temperature, and that is 13.5 degrees. It's a cold day here in Albany. It's the middle of winter, and we have some shocking weather lately, but I think that was probably the maximum temperature we've got today is about 13.5 degrees. But so what that means is the fact that at the Bureau of Meteorology, and I've been to the Bureau of Meteorology and when I was training apprentices in Kalgoorlie, Esperance, and now here in Albany, just to get and verify that all the data that I'm actually delivering in terms of the training is right and was correct, and it is. And I've used this chart many times over the years to show the students. We replicate the same theory in the classroom just so we can put a practical aspect to as to where they hear about this sort of stuff every day, but are not quite sure how it works inside. And it's based on how an air conditioning system works, so we try and add as many examples as to how these principles work theoretically in the real world, and this is one of those areas. So what we've got here is we have got a chart that I've used many times, and we've got a variation in temperature from 9.5 degrees to 13.5 degrees. The outside air temperature is 13 degrees, and we come across and they're saying that our humidity is 59%. Now I've just been on the Bureau of Meteorology's website, and they said that the relative humidity is 60 degrees Celsius. So that verifies the fact that, and all they got out of the Bureau of Meteorology, quite honestly, is one of those charts, because that's all they use at specific times of the day, the measuring and writing down the data. But they can't overcomplicate it because they want to have consistency, and the fact that these measurements have been measured in exactly the same manner right around the whole world, and so they can't change any of those parameters. So what we're going to do next is go and have a look at the Stevenson screen, and you'll get a better idea on what I'm talking about. But I just wanted to go through that process just to make sure you're happy about how that system works. Another thing before we go is the fact that they also measure the feels like temperature. So in other words, the temperature is 13.5 degrees, but on the Bureau of Meteorology, where I just had a look at, the wind at the moment is shocking. It's coming straight off the Southern Ocean, Great Southern Ocean, between here and Antarctica. And so the wind coming off is increasing the rate of evaporation of another thermometer that they use to measure the feels like temperature. And so that wind speed passing over that second thermometer, once again surrounded by water on its bulb, gives it enough speed, and the rate of evaporation is occurring fast enough to reduce the temperature dramatically. And in this case, they says even though the temperature is 13.5 degrees out of the Bureau of Meteorology, which is exactly what we measured here. It says feels like 3 degrees. And if you walked outside, and the reason why they say that is if you've got a large amount of air hitting you and you've got sweat on your face and the moisture on your system, the rate of evaporation will cool your body down so it feels like 3 degrees. So it's just another example of that latent heat of change, and another example where it's used beyond not only measuring humidity but the feels like temperature as well. Okay, so here's our Stevenson screen. That's what it looks like from the outside. There's a series of slats actually that have the capacity to allow air to be drawn in, and on the inside they should come back down again, so they're in a V arrangement. So the air is drawn in from the outside and then passes back down, so they can control the rate of flow passing through the screen itself. There's realistically only 2 measurements or 3 measurements they're actually doing. You've got the maximum and minimum temperatures, I'm not quite sure which is which, that occur through the daytime. So in other words, they're able to measure the maximum temperature and the minimum temperature. And the 2 that we were talking about is the humidity. So that there's no difference between this here in comparison to what we had on our kitchen sink. That is our dry bulb, and that is our wet bulb. As we can see, we've got a container of water down here, which is distilled water, passing up through a wick. Now that wick is surrounding that bulb on our second thermometer, and as the moisture or water is drawn up through that, it surrounds that bulb. And based on the rate of humidity, you're either going to have a greater degree of evaporation or a lesser degree of evaporation. The degree of evaporation is going to generate a huge reduction in temperature on this thermometer here. So therefore, the lower the temperature on our wet bulb, the lower the humidity. The lower the humidity, the greater the capacity that the air has got to absorb moisture. So it's a very simple apparatus. These ones at the back here are electronic versions of these 2 here. That's got our wet bulb, and this is our dry bulb. Like a lot of things that are happening worldwide, automation is taking over, and they can electronically sense these measurements without anyone having to go out to the box and measuring those 2 measurements. But that's just the overview of the Stevenson screen. It's been used, as far as I know, well over 100 years, and every location around the world that uses data by the Bureau of Meteorology worldwide use these Stevenson screens.